Hello, this is Opti471B. My name is Kevin Dupre, and in this lab we learned how to correct for distortion as well as calibrate the imaging system for spatial frequency response. In order to start out the lab, we first took off the lens and measured the pixel size, both for height, width and height. And in order to do this, we use the microscope objective to focus on one side of the pixel array, and then recorded that position, focused on the other, and then subtracted the values to find out the pixel width. We did this for width and height. For the next part of the lab, we had to measure the horizontal and vertical field of view. In order to do this, we took a meter stick and we put it at the full frame of the field of view, and based on this, we can get the field of view and angles by knowing the distance to the meter stick. From there, we took 20 different images of the checkerboard image at different orientations in order to get more accurate data. We then flipped the checkerboard around and took images of the slanted edge profiles in order to get an MTF measurement of the camera system. Then for the final part of the lab, we use a cube in order to try to measure what the angle of the two sides of the cube are. We know that it should be 90, and so judging by this, we can tell how well we calibrated the camera. And then also know.
Here we're going to show a brief overview of how MATLAB can be calibrated by using a collection of known targets or images identifying various key features. Once calibrated, the image may be corrected for aberrations, distortion, and other resolution issues. In our case, we used a large checkerboard pattern to calibrate the system. As can be seen, MATLAB identifies the largest inner square and then all the black to white corners. Once a collection of images, in our case 20, were collected, they were run through the MATLAB's built-in calibration toolbox. From inputting the square sizes of the checkerboard, MATLAB was able to calibrate how the grid was distorted and therefore the entire image. Sometimes, however, the automatic correction is imprecise and the distortion coefficient must be manually corrected. As can be seen here, even dramatic distortion from the fisheye can be corrected by very close to the original image. The physical interpretation of MTF is the distortion or blurred experienced by an object with a certain frequency. Mathematically, MTF is the absolute value of the normalized autocorrelation of the exit pupil, which is altered by the present aberrations. In order to analyze the MTF response using MATLAB, a slanted edge function was used as seen as in the top left. Due to the diagonal line, it is easier to see and quantize the MTF, or practically speaking, sharpness of the picture quality.
This is the error analysis for the IEEE 1394 camera, which is not the fisheye camera. This is before optimization and after optimization. Notice that the error in pixels is much more tightly grouped after optimization. These are before and after images of the scene. You can see that there's slightly less distortion in the scene over here. These are the calibration results. We were actually unable to achieve the 0.1 pixel error before filming the video. There's their example images. This is with the box using the extrinsic image tool, and this is one of the 20 images, just an example image. These are the MTFs. Here we have the top left corner of the picture and the top right slant edge. And here's the bottom left and bottom right. And here's the center. Notice that the top left seems to be the higher performing MTF. Here are the fisheye results. The files were corrupted and we were only able to obtain 2 of the images. But with these images we were able to achieve a less than 0.2 pixel error. For fun, I own a GoPro, which has a high field of view and produces some pretty distorted images. So I calibrated it using the same procedure as in lab, taking 20 images of a checkerboard pattern. This is a before picture, and this is an after picture. And these are the specs for the box, column vector 1 and 2, and after doing the dot product, we found that the angle between the two faces was about 88 degrees, and this is the vertical field of view and the horizontal field of view for IEEE 1394, and this is for the fisheye, which is what we expect a higher field of view for the fisheye lens.